we've now finished chapter 1, which is really just sort of the basics. It sets the tone for a lot of what we'll be needing this year in terms of algebraic stuff and also domain arrange and those sorts of things. The next chapter, chapter 2, is all about polynomials and what we can do with polynomials. So before getting into sort of the general form of polynomials, we'll start with section 2.1, which deals with quadratics whose graphs are parabolas. So we're going to be spending today just kind of going through some review of quadratics. Now in Algebra 2 or Algebra 1, when you first see this, usually this unit's about a month long. So I'm really just going to try to highlight the key points and boil them down to a single lesson. All right. So to begin with, let me just kind of remind you all what I'm talking about. So the standard form, as it's called, for a quadratic function looks like this. F of x equals ax squared plus bx plus c. In this form, a, b, and c are all real numbers. And we also have to make sure to say that a does not equal 0. If a was 0, then we wouldn't have the x squared term. It would no longer be quadratic, and we would just have a line. So this is what I'm talking about. Now the graphs of these look something like this. Let's do an xy axis here. So there's a parabola. Alternatively, it could be narrower or wider, and it could be upside down as well. So we would say in this case, these parabolas, they open up, we say, and this one opens down. All right. Now the first thing I want to mention about the graphs is that the a value actually determines how wide it is or if it opens up or down. So for example, let's say this was an a value of 1. This blue graph would have to have a larger a value, something like 2 maybe. Because it's narrower, it kind of means that the slope of the line tangent to that graph is steeper. So we would say a is a larger number. And then if it opens down, that means it's negative. A is negative. And so, for example, maybe this one, it looks like it's about the same narrowness or width as the black graph over there where a was 1. So we could say something like a might be -1. Now these are not, you shouldn't be able to just know these exact numbers off the top of your head, but just as a point of reference, I'm showing you that the blue graph has a larger a value because it is narrower. So that's really the key takeaway here. It's not necessarily the case where you're going to look at a graph and say, oh, I know a is 2, and then move on from there. I'm just pointing out that it's a larger a value. And same with this value over here, a is negative because it opens down. It's sort of an upside down parabola. Okay. All right, so that's the first concept. You're going to have a Delta Math question which sort of asks you this. It won't give you any numbers. It'll just sort of say what is an appropriate value for each of these graphs. And so you'll need to know if you have a larger a value, it's narrower. If it's negative, it opens down. That's really all you need to answer that question. All right, let's look at a more specific example just so we can identify some key features of the graphs of parabolas, which is my first objective, being able to identify key features. So let's go ahead and let me actually do a graph of a parabola. Let's say it is over here. And then let's say does this. Okay, obviously not drawn to scale, but let's say this is my parabola. So the first thing I want to discuss is the domain and the range. The domain of the graph is all real numbers. This is true for every parabola. I can keep going left and right forever and I won't ever have an issue. The range, however, is always going to be limited. So notice if we're looking at the y values, we start at 1 and we go up from there. So that means the range is actually going to be 1 to infinity. The next two vocab words that I want to bring up are specific to parabolas. So for example, the vertex. The vertex is this point right here. So the vertex is always either the minimum or the maximum value, or it's kind of where the two sides of the parabola come in and meet, where the parabola changes direction. So the vertex in this case, oh, I don't know why that's a negative there. One sec. -2. So the vertex in this case is the point 2, 1. And we would say that the max or the minimum value of this parabola is y equals 1, and this happens at x equals 2. So the x equals 2 does not really tell you the maximum or the minimum. The minimum value is y equals 1, and that happens at x equals 2. Okay, the last thing I want to mention is something called the axis of symmetry. So if you drew a line through the vertex, a vertical line, this is the equation x equals 2 here. Notice that that's sort of the line of reflection for the parabola. If you folded it around that line, you would have all those points meeting each other. That is called the axis of symmetry because it is symmetric around that line. Notice now you can't just say 2 though, you have to actually say the equation is x equals 2. If you just said 2, you might mean y equals 2, and y equals 2 is a horizontal line, not a vertical line. Okay, so let me just double check that I've covered everything I wanted to. Yes. I do want to mention one other thing. We're going to see a lot of different forms for parabolas. We're going to see 3 total different forms. One component to each of those forms, though, is consistent, and that is that a value. So I'm going to give a special name. So in the equation y equals ax squared plus bx plus c, this was the general form. This a is, well, first of all, a, b, and c are all called coefficients, but in particular, a is called the leading coefficient because it's sort of the first coefficient we see when this is in general form. And this concept will come back, so if you're not quite getting this, just know that a is called the leading coefficient. So when I refer to the leading coefficient, I'm talking about a. All right. So hopefully that was a good little reminder of parabolas and quadratic functions in general. We haven't really done anything specific. We've just kind of defined some vocab words. So now let's get into an actual example where we graph. So let's go ahead and graph the function q of x equals x squared plus 4x minus 5. All right, now this example is also intended to remind you of a couple of other tools in your toolbox when using quadratics. So I'm not going to explicitly sort of teach you those separate from the graphing. I'm just going to combine it all into one example here. So when you graph, you need the y-intercept, the x-intercepts, if they exist, and also the vertex. So those are the sort of the key points, and then once you have the vertex, you also need to have sorry, never mind. You need to be able to identify the axis of symmetry. I was going to say to include it. You don't need to include it. So we'll say identify axis of symmetry. All right. So let's go ahead and work these out. So first of all, let's do the y-intercept. So the y-intercept, for every single function you ever come across, you set x equal to 0. If you don't have that written down somewhere, I would recommend doing so. And then you solve for y. So let's go ahead and set x equal to 0. We end up with -5. And so that means that my y-intercept is 0, -5. Okay, we're going to use that. X-intercepts. Now for the x-intercepts, you always set y equal to 0. So that means I'm solving 0 equals x squared plus 4x minus 5. Now in order to solve this, you have to factor, or if it does not factor, you can use another method, which we'll come back to. In order to factor, you need to find two numbers that multiply to -5 and add up to 4. So that would be +5 and -1. So my factors are x plus 5 and x minus 1. You can always double check that this works by distributing. And so then solving for x, you end up with x equals -5. I noticed a couple of you weren't switching the signs when you solved. You set them equal to 0, the factors equal to 0, so you get opposite signs. So I get x equals -5 and x equals 1. That means my x-intercepts are -5, 0, and 1, 0. Okay, so those are the intercepts. Now the vertex is going to be a little bit more involved. And this is going to kind of take us off on a tangent. So don't forget that we are trying to graph this function, but like I said, I'm going to be using this as a teaching opportunity. So for the vertex, when it's in general form, you really need to use completing the square, although we'll sort of take a shortcut when I'm done with this. And what completing the square means is that I have this function x squared plus 4x minus 5. What I want to do is I want to make this a perfect square. And so in order to do that, I have to figure out what to add to it in order to make a perfect square. So let's kind of review some of the perfect squares. If you have x plus 1 squared, you get x squared plus 2x plus 1. Excuse me. If you have x plus 2 squared, you get x squared plus 4x plus 4. You could work all of these out on your own as well. This would be x squared plus 6x plus 9. And so continuing that, you'll see there's a lot of different perfect squares. Now notice I have x squared plus 4x, which is actually what I have here. So that tells me I need to add 4. So I'm going to do x squared plus 4x. I'm going to add 4 to that. But you can't just add 4 to something because it's now changed the expression. So if I add 4, I also have to subtract 4 to balance it out. Notice if you were to combine like terms, you would just end up with that -5, but we don't actually want to combine like terms, which I'll show you in just a moment here. Oops, trying to color code. All right, so let's now take a look at x squared plus 4x plus 4. This actually equals what I had up here. This is x plus 2 squared. And then -5 minus 4 we'll just say is -9. Now I've actually changed my function to a new form. This is equivalent to the other one I had, but this form gives me the vertex. So this is actually called vertex form, if you remember that from a previous class. The reason this is useful is because it actually tells me the vertex right away. Notice that this equation here is a transformation of my parent function, which was y equals x squared. It's a transformation left 2 and down 9. So this actually tells me that the vertex, which starts at 0, 0 for the parent function, is going to go left 2 and then down 9. So that means that the vertex is -2, -9. And now we have all the pieces we need in order to actually graph. So let's go ahead and do that. My vertex is -2, -9. My intercepts are at 1 and -5. And then my y-intercept was at -5, I believe. Let me just double check that after I graph it. I think it was -5. Yep. So my graph ends up, and let me just double check everything, -5, 1, 0, yep, looks good. So my graph ends up kind of looking like this. You could check this in Desmos as well. And then we could say the axis of symmetry is x equals -2. All right, so that brings us about to the end. This video is starting to get a little bit long. I'm going to do another example of this in the next video, and then we'll also see some more forms, vertex form and factored form, to help us out with graphing. But this was really just kind of the preview, hopefully jogged your memory a little bit with quadratics.